Hi guys, welcome to week 6, and I apologize for the Buzz Lightyear reference up top, but to me every time I'm teaching limits to infinity, when I say to infinity you have to say and beyond. So anyways, what does this mean? Like, what are we going to be doing? Well, we talked about limits last week with looking at a graph and what is the y value approaching, right? So the idea is we are still looking at what y value are you approaching. Ooh, we need a pen. Hold on. There we go. Okay, so we still need what y value. Something weird's going on. What's happening? Stop thinking. Hold on, it's doing something crazy. I don't like it. Okay, I think we're good now. I think we're safe, everybody. Whew! Alright. What y value is your graph approaching? So that's still the same, okay? What y value is your graph approaching? But now, instead of x approaching a numerical value, it's as x is approaching infinity or negative infinity. So in other words, as x gets bigger and bigger and bigger, what is happening to the y's? For a lot of people that understood this well in pre-cal, I'm pretty much asking you for end behavior of a function. That's all this is. What is the end behavior? And you have a choice as to how to do these. You know, some people do them graphically, some do them numerically, and some just memorize rules. So we're going to kind of hit on all those, I guess, a little bit. But first, let's start with graphical versus numerical, if you wanted to do this. So I'm going to pick something like, let's say that you're given y is negative x to the fourth minus 3x cubed plus 2x plus x minus 1. Okay, I don't even know. So I do not know necessarily what this looks like, but I do know this. If I want to analyze this graphically, I can, because we learned last year that you look at the leading term, and this is going to tell you the shape of the graph. We know that this graph, since it's a negative, it's going to be reflected, and since it's x to the fourth, it's going to be just like an x squared. So it's going to be like an upside down parabola on this side and upside down parabola on this side. Now, all this junk, maybe it does like funky stuff. I don't know. Maybe it does that, but maybe it just looks like a parabola. So this part in the middle, it don't matter. And if you don't like my grammar, you can correct it. It's more fun with bad grammar sometimes. Okay, this part in the middle, it don't matter, because we are looking at if they asked us the limit as x goes to infinity for, you know, this equation up here. I don't want to recopy it. Okay, for all of that, if they asked us this question, all we care about is, okay, the biggest x on this graph is going to be approaching what? So if I look at my picture and the biggest x will be somewhere over here, this graph's going down, babies. And if the graph's going down, it's headed towards negative infinity. Now, please don't answer does not exist. I've had some students that say, oh, well, it's heading to one of the infinities, so we should call that the limit does not exist. If they, and this is how I remember it, if they can use an infinity here, then I can use an infinity here, okay? And that's how you know when you're allowed to answer with infinity versus a does not exist, okay? So that's pretty much how it works graphically. Now, if you wanted to analyze this numerically, I am not a huge fan of this, but it makes sense for a lot of people. If you're quick with numbers and good with numbers, numerically is the way to go. Pretty much, you just mental math it. You mental math by plugging in a relatively large x. A relatively large x value. Now, you can't actually plug in infinity, right? But you also don't want to plug in a million. I mean, who can math that out, okay? But I picked something like, for me, a relatively large one is like 10, because usually a graph, by the time you get to 10 on the x-axis, a graph knows what it's going to be doing. So I picked something that I can reason out, and I'm like, okay, so I've got negative like 10 to the fourth. So that's a pretty big number. That's like negative, is that 10,000 or something? And then I'm going to minus 3,000, so I've got an even bigger negative number. I'm going to add 20, which doesn't do much. I'm going to add 10, and then I'm going to minus 1. So this was a really low negative number. It's like negative 9,000 blah blah. No, it was 13ish. It's around negative 13,000. So you get the idea though. You plug in a number and see where is that number going. Well, it is going there because it's a negative, really big number negative. So that's kind of how you can do it numerically. Now, that I would do something like this anytime it's a normal function like a polynomial. Maybe you've got a square root going on. Use your knowledge of parent functions to answer this kind, okay? Use knowledge of parents or parent functions. Because if you know the shape of those graphs, that's going to actually be pretty dang easy. Now, the ones that you're familiar with that we actually did a couple weeks ago are the rational functions. And if you are asked about a rational function, like the limit as x approaches infinity of, let's say it's, like 3x minus 1 over x squared plus 6. Okay, if it's something like this, then if you're just looking for the, like I said above, the end behavior, which is pretty much what this is asking, is what's happening on the right side of the graph. If you're looking for that, you can totally do that because we learned how to find the end behavior asymptotes a couple of weeks ago. So what were the rules on an end behavior asymptote? Well, on something like this, the denominator in the bottom is bigger, right? And so that means that it's 0. So if the end behavior asymptote is approaching 0, then guess what? The answer to this is also 0. That's going to be where the asymptote is. And if you were to graph it on the calculator, you would see the graph's trying to approach 0 as it goes to the far right. Now, if you ever see them do negative infinity instead, okay, I don't want you to get like crazy about it, especially if it's a rational function, because it's not a huge difference. Okay, so this just means what's happening to the graph on the left side instead. Well, here's the deal. If it's a rational function and it has an end behavior asymptote, that asymptote goes across the left side and the right side of your picture, right? So it should be the same for either one that they ask you. Now these have powers that match, so what do you remember about that? Well, powers that match just mean you reduce and you get your answer of 3/5. So not bad at all, I hope. Now, what's the only other tricky kind? Okay, I have seen one other kind of tricky kind, and that is one that's maybe like this. Something like that. Okay. I have seen ones like this where it is a rational function because it's written as a fraction, but in the denominator you also have another parent function thrown into the mix, and that freaks people out. So what I told my students is it actually works to still compare the powers. You just have to think a little bit. In other words, like 2x is 2x. Okay, not much you can do with that. Now the highest power on the bottom, it's not an x squared, guys. It's not, because it's under a square root. So kind of think of capturing all that together, and now it's the square root of x squared is really like an x, so the powers actually match in this one. So when the powers match, you're supposed to take their coefficients. So on the top it's a 2. Now be careful, because you're not going to take just a 3 on the bottom. You're not. You're going to take the square root of 3, because it is still under a square root. So that's kind of how that would work. I just kind of want you to have a heads up on that, in case that kind of problem shows up. And that's how it's going to work. So, and the only other rule I didn't cover, so larger on bottom is always 0. If they match, you just do that, okay? If it's larger on the top, so limit approaches infinity, and maybe it's like 3x squared plus 1 over x plus 1. Okay, if they give you this and it's larger on top, then that's going to be a slant in behavior asymptote. Now, all you have to know, guys, is which way is it slanted. And if you kind of mental math this, and reduce that, you're going to get 3x. Well, the graph of 3x looks something like that, right? So if this is asking about x going to infinity, it's saying what's happening on the right side of this graph. Well, it's going up. Yay! And what if they had changed this to a negative? Well, think about the left side of this graph, and it's going down. So all you have to do is really analyze this and reduce it and know what that line is going to kind of look like, and then you can say infinity or negative infinity. So I'll try to stump you with some either on the practice or in tutorials, but that's the main idea there. And the last thing is checking continuity from an equation. So this would be like to see if something is continuous or not, you want to make sure there's no holes or gaps or asymptotes. And the way that we should do this with an equation is we should really remember that a hole is when something factors and cancels. And what kind of discontinuity is that? Do y'all remember? Removable, non-removable, or jump? That one would be the removable one. And then the only other thing you're going to really have happen to you on a normal equation is going to be if there's a vertical asymptote. So if there's a vertical asymptote, that would be terms that are left in the denominator that didn't cancel, right? The terms that don't cancel. And those are called non-removable. And the only time that you're going to get a jump, okay, the jump continuity is if you have a piecewise function, piecewise that doesn't align. And is align 2 L's or 1? Oh, that's embarrassing. I can't remember. This looks right. Align, A-L. I don't know. It may be 2 L's. I'm sorry. Okay. So if a piecewise function doesn't align, it could be a jump, or it could actually be, it could also be removable. You just have to be like super careful. So an example of that would be like f of x, blah, blah, blah. Maybe it's like 3x minus 1, x is greater than 2, 2x squared plus 1, x is less than or equal to 2. Okay, so let's say that you have a function, a piecewise function given to you, and they want to know, is it continuous at 2? And if it is, great. If it's not, what kind of discontinuity is it? So the way that I do these is I actually don't take the time to graph it in its entirety, but I do think about the graph. This is a line, and so it's going to be a line when we're bigger than 2. And then this is going to be a parabola whenever we're less than or equal to 2. So it's going to be some kind of parabola that runs into some kind of line. It looks something like that. Now the question is, do they actually meet up right there like I drew it, or is there a gap? So how do we figure that out? Well, the easiest way, I'm going to put the or, okay? The easiest way is to take that number right here where you've restricted your domain, plug it in to each function, and see if you get the same y value, right? So it's almost like you're checking for a limit. So you plug in the 2, and here I get 5. If I plug in the 2 here, what is that? I get 9. So this one stops at 5, and this one stops at 9. So it's actually like a line below this. It looks something like that. So there's a definite jump there. Jump discontinuity at x equals 2 because they don't meet up. Okay, if they had met up like that, then you would say, oh yeah, they were the same y value, so they meet up. So yay, it's continuous. But that did not happen to us. So we would say jump discontinuity at x equals 2. And that is how you check for whether or not you're continuous with a piecewise. And these other two, I'm not going to do an example of because I feel like we did a lot of those a couple weeks ago. So you could go back and look at your notes on what makes a hole and what makes a vertical asymptote, and then use that when doing your practice problems this week. And that's about all I can think of. So good luck with the practice problems, and then I'll come in and we'll see if you got them right.